And if I keel over and fall down, somebody call the ambulance. Okay, what we're going to do today is this is actually the last lecture on a topic that you might some might consider part of networking, but some might consider part of a more general topic of distributed systems. So it actually forms a bridge between the stuff we learned about in networking and what we're going to see from Wednesday over the next 6 or 7 lectures of the class. And the associated recitations having to do with fault-tolerant, reliable computing. And most of the interesting aspects of what we're going to talk about there have, involve techniques in fault tolerance, involve techniques having to do with redundancy and replication. And DNS, the domain name system, which is the system we're going to look at today in the context of distributed naming, is a bridge because on the one hand, it covers some of the aspects of networking that we talked about. On the other hand, it shows an example of how you can achieve replication to talk about to achieve fault tolerance. And we're going to study these techniques systematically over the next few lectures. So getting an example in mind is usually a good idea. So you've already seen the network layer, and you've seen that at the network layer, attachment points on the network are identified by IP addresses. In the internet, or more generally, identified by network layer addresses. So as an example, on the internet are IP addresses. And this is the name that's used by the network layer to identify attachment points anywhere on the network. And in fact, is the name that's used by the end-to-end layer to name one endpoint of a connection. So in fact, if you think about it and go back to our very early lecture on naming, an address is really just a name, but a name that's been overloaded with information that allows the user of that name to locate this object. So an address really is a name that has information in it, overloaded information in it, that actually allows for it to be located. And in fact, an IP address is nothing other than a name that tells you where in the internet topology the entity being named by this IP address is located. So, MIT's, my computer is something like 18.31.0.35. It doesn't mean anything other than the fact that somewhere on this internet topology there's this big, complicated graph, and that address allows you to do routing in the geography of that topology. It has nothing to do with real-world geography. It just allows you to do routing in that topology. Now, in principle, you could build every internet application and have users interact with internet applications purely with these network layer addresses, but that would be quite inconvenient. I mean, you would then have to be sending email to your friends, not with joe@mit.edu, but you'd have to do joe at some IP address, and it's pretty hard and complicated to remember. So the first problem with just using pure network layer addresses that we want to solve today, and we will solve to some degree, although not completely, is to come up with a better way of naming things that are more convenient. And you already know the answer. The answer is you don't send mail. You send email to joe@mit.edu. You go to the 6033 website as mit.edu/6033 or some other equivalent thing that leads to the same page. You don't actually think about names in terms of IP addresses. So in fact, to a large extent, the fact that these are human-readable, human-understandable, and names that are mnemonics that you can easily remember is a good thing. And so we actually do want to come up with a way of naming things that's independent of IP addresses. The second goal here is to come up with a naming scheme with a solution that allows some degree of modularity. In particular, provides, as you know, names provide a level of indirection between the thing that you want to get to and the thing and how you want to the handle that you want to associate with it. And that level of indirection, if we come up with a good way of doing this, it will allow us to do a few things. Like, for example, I can tell you that the website for mit.edu for the MIT for the institute's homepage is mit.edu, and underneath, behind that, I could change the actual computers on which the website is located. And I could do that independently of telling other people of any change in it. Whereas if I told them that the website was at a particular IP address, then every time I moved a page, moved pages from one computer to another, I'd have to tell everybody in the world that the website has changed. And we'd like to minimize doing that kind of thing. And so the domain name system provides a solution to this problem, or DNS provides a solution to this problem. Most of you have already heard of this. It maps between what are formally called domain names, but what we're going to just call host names for convenience. It maps between host names and records. And it turns out there are many different kinds of records, and we're going to look at a few of them in this lecture today. But for your mental model right now, just assume that it maps between host names and IP addresses. So it turns out that an IP address is just one example of a record called an address record. But the general goal of DNS is to map between host names and records, and there's a variety of them, as I said. For now, just assume they're IP addresses. So for example, mit.edu might be 18. Whatever it is as an IP address. So what are the goals in designing the system? So primarily, we're going to be talking about how the domain name system is designed and how it works. And as we go along, we'll see some things that it does that are different from other systems or other ways you could solve this problem. The first goal, there are basically two goals in the design of this system. And the first goal is that it should scale. In fact, the original motivation for the domain name system when it came about in the early 80s was that it was becoming extremely inconvenient to manage the mappings between names of hosts and their IP addresses in a way that, as the network grew, and it was growing pretty rapidly even then, as the network grew, it turned out to be a management nightmare. And to understand this, basically there's three ways in which you could imagine doing, there are more than three ways, but there are three more obvious ways in which you could imagine mapping between these names and these records, or names and IP addresses. And the first one is, in fact, the way the internet names were being managed until DNS came along. And that's to use a model that you might think of as the telephone book model. It's actually astonishing that even today, this is the telephone companies use the telephone book model, where every 6 months at your doorstep, there are these 3 thick books that show up. And you're just looking at it and going, what do I do with this? And you log into your home, and by the time you might use it a couple of times, and then the next big 3 books come along. You actually wonder why they don't just put their phone books on the web and make it easy to get at. But the telephone book model really is, there's this central repository of information, and everybody gets this information from the central repository, but the repository actually pushes it to everybody. So it's not really a queryable repository. It's not something you go and contact on an as-needed basis. So in fact, every few months, or in the old days of the internet, every day in the morning, every computer would go and pull the current mapping between names and addresses from a central site. And this model, kind of works for a little bit, but stops working. It stops scaling on multiple levels. First of all, the resources required for everybody to, have to go and collect this information every day turns out to be significant. But it also turns out to be a scaling bottleneck more fundamentally from the standpoint of any time you add a machine to your local, to your organization, you have to go and tell the central person that you've added this machine. And so at a human level, it doesn't scale very well, because you can't allow for this to automatically happen, because then people will sort of willy-nilly do all sorts of, just claim that they own various machines or various names at various places. So the telephone book model is something that the internet used to have. It used to be a file called hosts.txt, and every computer had a copy of this file that usually was current as of a 24-hour period. So the second approach that you could adopt, knowing that this approach of just sort of pushing a telephone book periodically doesn't work, is you might actually adopt a model, a centralized server model. And the central server model is, the main difference from this telephone book model is that this thing nothing is pushed to you. Instead, imagine a search engine like, say, Google or something like that, where if you want to know the mapping between a name and an IP address, you go and contact this name service. which turns out to be a central server, and it does essentially the same thing that Google might do. And this actually isn't that hard to implement from a technical standpoint, because Google does much more than this, and clearly it works. But the real problem with the central server model is what I alluded to the last time. It doesn't handle when you assign names to machines, you want to make sure that people don't conflict on these names, because these are well-defined names for machines on the internet, and you need a model by which you can decide who's allowed to name a machine as foo.mit.edu and who's allowed to take x.cnn.com and so on. And so for every computer on the internet, having a central person deal with deciding whether that's okay or not isn't a scalable solution, and that's why we don't really adopt that model for DNS. And the model that's adopted for DNS, and it has a number of other attractive properties, which we'll talk about, is the distributed database model, or more generally, a federated model, where every organization, and organizations could be recursively defined to have sub-organizations, every organization sort of manages a portion of this overall global namespace, and it manages everything about it. It manages all of the mappings between names and records for that part of the namespace. And the more names they have, the more work they have to do, but nobody else really has to do that much more work. And it's a pretty nice model, because everybody does some amount of work in terms of technical resources, and more importantly, in terms of human administrative resources. And overall, that really that's one component to the scalability of the system. And that's one of the main reasons why the system turns out to scale and work very well. And the second goal is reliability. Once you have a system like this and people start getting used to it, and applications start using names, it had better be the case that the system is in fact generally available. And it better not be the case that the DNS be the Achilles heel of the internet in terms of, the network infrastructure has a very, very high reliability because all this routing stuff works out great, and we find all these alternate paths, and things don't work because I'm not able to get to my DNS. That had better not be the case. So we'll see what techniques DNS uses to get pretty good reliability. Though the jury is still out as to exactly how reliable it is, but overall, I think most users will admit that generally it seems to work about as well as the rest of the network. So what does DNS do? Fundamentally, it provides an abstraction called a lookup abstraction. You give it a name, it returns a record to you. And you can ask for particular types of records that you want, and we'll get into that in a second. So you ask a name, and you get back a record. And there's many ways, and different operating systems have different ways in which this exact function is called. For example, get host by name might be a commonly used way of going from a name to an IP address. But we're going to just say DNS resolve, just more abstractly. So an application can invoke DNS resolve DNS name and get an IP address or some other record associated with it. Now, if you think back at the way we did our idealized naming model, or a generic naming model, we actually had a resolve which took a name and a context as an argument, and it returned back the value that was bound to that name. So you might ask what the context is for DNS resolve, and there's actually multiple answers to this question. The first answer is that applications specify a context usually. So for example, an application might specify that it wishes to know the IP address of this name. For example, if it's a web browser that wants to know some server's IP address, so it can connect to it using a TCP connection. Alternatively, an application like an email program might specify that it wants not the IP address of this machine, but the name of a machine that can handle mail on behalf of this name. So for example, if I send somebody email to abc@mit.edu, my mail program, somewhere along the way, some server would do a lookup for a special kind of a record, turns out to be called the MX record, which is a mail record, which would then return to me not return to the caller not the IP address of mit.edu, but the IP address of, in fact, return a name of a machine that's capable of handling mail for mit.edu. And in general, that would be very different from the IP address associated with mit.edu. So, that's the kind of record, and that's established as a context. And more generally, there's a DNS configuration file. There's some DNS configuration or a registry or whatever it is on, depending on the system that you have, that tells this resolve step what context in which the name must be resolved. So just for example, you might have a machine cricket.mit.edu, another machine cricket.berkeley.edu, and DNS resolve might call, DNS resolve of cricket. And your application needs to know, and when the application calls that, the person doing the resolution, the program doing the resolution needs to know what context to do it in, and often that's specified in the DNS configuration. So, on Windows and Unix, you can, there's this thing called the search path, and you go through a set of search paths that provide this context. So we'll see this in more detail later today. Now, users themselves, and there's an important point here about lookups and how lookups are to be distinguished from something else that I'll call search. Now, these names are generally very useful for programs because they allow modularity to occur, where no longer are you worried about services being associated with IP addresses. You could move your website between IP addresses at the back without telling everybody about it. So from that standpoint, this name-to-record mapping of DNS with lookups is very, very useful. In terms of convenience, the DNS is not the whole story, because although you most often send email to people with foo@mit.edu, so you remember that, or you have some other file in which you find that information very easily. More generally speaking, people often don't need something in addition to just lookups. Human users need something in addition to lookups. And the general term given to that is search. So for example, Google provides search on the internet, and tomorrow's recitation talks a little bit about one aspect of that. And in fact, it's an interesting discussion, because you'll find for the reading for tomorrow that users were using a search engine to essentially do a lookup task, where they would go to Google and type CNN.com. When in fact, if they already knew CNN.com, they could just as well have typed it on their URL window, and that's sort of the way in which people are, real users have turned out to use the web. Moreover, peer-to-peer applications that some of you or most of you might be more familiar with than I am have a form of search, and those applications are interesting because they do searches on all sorts of attributes of the content that you want, and by and large don't really use DNS in a particularly, if they use it at all, it's sort of incidental. They probably don't even need to use it. So it's not like all internet applications require DNS in order to work. In fact, there are plenty of applications that don't need DNS at all. And they benefit a lot from search. Okay. So let's get back to DNS and talk a little bit about a few different topics. We're going to start first with the namespace and how it works, and then we're going to talk about how name resolution works, and then we're going to talk about things like performance and scalability and robustness. So the DNS namespace has two properties to it. The first is, and both of these are nice ideas and hit upon a theme, or at least one of which hits upon a theme we've covered in 6033. DNS is a hierarchical system, and it's a structured namespace. I'll describe what structured means in a moment. So the way DNS namespace works is it's a hierarchical system which is structured as a tree, and at the top of a tree there's a little circle which really is a dot, and I'm going to call that the root. So everything starts at the root, and the root is the root of this namespace, and it's a tree. Now the namespace is divided into a bunch of domains, and domains are divided into subdomains, and subdomains are recursively divided into sub-subdomains, and so on. And in fact, the depth is arbitrary. It could be arbitrarily long. In practice, nobody really has need for a depth more than 4 or 5. And in fact, 90% of the names, or more than 90% of the names, are pretty flat. You don't go more than 2 levels down. So at the top level, and this is probably familiar to most of you, you would have com and edu and net and org and gov and a few others. And these things, there's 7 or 8 of the, actually about 13 of them right now. These things are called generic top-level domains. So the generic in the sense that they're not really associated with any country, for example. And then in addition to this, you have a whole bunch of country codes like .us and I don't know how many countries there are, but there's a large number of them. So those things are called country code top-level domains, and they're not that interesting in that there's nothing different about them from anything else. So we may as well just look at the generic top-level domains. Okay, and edu gets divided into MIT and other places that don't matter, and so on and so forth. So you might end up down here. You might have www for our website or for whatever the students run. I don't know who actually owns this. CSAIL might be here. EECS might be here. And I might have a machine underneath here, let's say X, well, just a random machine. And the thing about the DNS namespace is that every label here, this is a label, right? So the way you read this is that if you just start at any label here and go upward, you can read it out from bottom to top. So you could say com is an example of a label, MIT edu root is a label, so that's read as mit.edu dot, and usually people omit the trailing dot because it's implicit, or you x.csail.mit.edu dot is another fully formed, or also called fully qualified domain name. Okay, that's sort of the correct way to read it out is from bottom to top. Now, every node here is associated with some information, and that's what this record means. Some nodes might have nothing in it, but in general, every node is associated with some information. So for example, X might have information here. I'm just going to call it INFO for now. But X might have associated with it an A record, which is an IP address record. I'll describe that in a moment. But it might have other things associated with it. In fact, DNS is pretty flexible. You could define your own record and put that into the system and have applications that read from it. It's pretty opaque to it. It doesn't really require, if you have something new that comes up and you want to use it, you could stick it into DNS and retrieve it out. So people put all sorts of things now into DNS. For example, there are weird proposals. Put in GPS coordinates of a name. That could be useful. So if MIT.edu isn't going to move very much, then put in the GPS coordinates. You might find applications that find it useful. For example, if you're, some mobile computing application might find it useful. So there's all sorts of things you could stick in to the DNS, and people have come up with all sorts of very wacky things, including telephone numbers in DNS. So, it's very flexible. So not only are the leaves associated with things inside, with information, but you can have information at any level. Any node in the tree has information associated with it. And the scale of this namespace today is extremely big. I mean, I don't know the exact number of things there are, but I've read that about 500 million, I don't know if it's 250 million or 500 million, somewhere in between, names have been, there are that many registered names in the system in aggregate. That's a pretty big number. Now, that's a very big number, so you need a way in which you can make the system scale, and that's done using a really nice idea called delegation. And more than any technical decision that was made in DNS, I mean, we're going to talk about some of them like caching and all of this other stuff, but more than any technical decision, delegation is really the reason DNS scales, and ultimately really the reason why DNS is pretty successful. So what is delegation? The best way to understand it is recursively. So the root at the top is centrally owned, and it's owned by a trusted entity. So what that means is that any name that ends in root, ultimately the authority for that name rests with whoever owns and runs root. And if you've paid attention to the press and to newspapers or magazines, you'll see that there's this fight for the root that's ongoing right now over the past few years. And the current owner of the root and things associated with it and who essentially controls the namespace is an entity called ICANN, ICANN, and there's a lot of politics associated with it. Now, continuing down on the delegation idea, the next layer down from the root, the technical term for it is a top-level domain, because it's at the top level. TLD. Okay, and these top-level domains are domains that are delegated from the root, and it's really hard to come up with a new top-level domain. I mean, in addition to these, you have a few more, but you don't really come up with them willy-nilly. You kind of have to go through a long procedure before the root decides to delegate a top-level domain to somebody else. And now it's recursive from here on. Every label here can be sub-delegated arbitrarily by only contacting the owner of that label. So once you get to com, you don't have to go further down. You just have to go to whoever happens to own .com, the com label, and tell them that you want to register a new portion of the namespace with that. So for example, MIT must have gone at some point to the owner of edu and said, I want MIT, and there's some out-of-band human procedure that occurs before the other party is convinced that this MIT is, a legitimate entity and allocates this name to it. And likewise, whoever wanted CSAIL went to the person who runs MIT's name. This is called a zone. So this part of the DNS namespace, and told it that it wanted CSAIL, and established by human efforts rather than anything technical that it wanted that portion. Now, the reason it scales is that you can kind of add machines at the, names at the bottom, not machines, but names anywhere here without really having to go all the way up. You just need to go up to whoever owns, your parent label and convince them that you want a name. So if I want to add a machine Y, I don't really have to go and talk to even anybody at MIT. I just have to talk to the person who runs the CSAIL namespace and tell them that I want a name Y. And I can then sub-delegate that name. I could today connect a computer, x.csail.mit.edu, have an IP address with it, and tomorrow decide I don't really want X to be a computer. I want it to be, the name of my research group or whatever, and then have machines underneath it which are y.x.csail.mit.edu. What I do with the label is my business, and there's no rule that these are IP addresses. In fact, these are nothing. These are just labels, and I can associate arbitrary amounts of information I want with that label. So domains can be formed anywhere in tree. And that's really nice, because you don't have to go back to a central entity in order to add these names, and that's the main reason why the central server model doesn't really fly. Okay. So examples of records. We've already seen a few of these, so let's look in more detail at what this info could contain. And like I said, it's very flexible. You could have all sorts of things you add in here, but there's a few very common ones. The first one is called an A record, which stands for an address record, and it's what you might expect. It's an IP version 4, address for a name. So x.csail.mit.edu, whatever its IP address is. So that's stuck in this database. It's maintained in a file on the name server that handles that name. You might have MX, which stands, the X is for mail exchanger, so it's mail exchanger. So that's for email. So when I send email to you@mit.edu, somewhere along the way there's a lookup done for not the IP address of mit.edu, but the MX record for mit.edu. And in general, that MX record could be anywhere. If MIT decided to outsource its email functionality to some other company, the MX record would just point to some name of a mail server in that other company. So it doesn't even have to be local to us. There's another one that's interesting in the context of stuff we've seen before called a CNAME, which stands for a canonical name. But a CNAME is really a synonym. This is where you can say there are many names that really mean the same thing. So for example, to take a very real example, when there used to be AI lab and LCS, and now there's the same lab, CSAIL. Now there are a lot of subdomains from lcs.mit.edu and ai.mit.edu, and it's a nightmare to have to go and change all of the DNS entries for all of the machines. So the standard way in which you manage this kind of thing is to set up these CNAMEs, which says, my research group is nms.lcs.mit.edu. That's what it was. You just set up a CNAME that says nms.lcs.mit.edu. There's a CNAME for nms.csail.mit.edu. So you don't have to do anything more other than set up these synonyms, and everything else just sort of continues to work out. And there are other useful names, useful things you could do with CNAMEs. For example, if you decide you're running your email or your web server on one machine, and then you want to change it over to another machine, but not have to tell the whole world about it, what you do is you tell everybody that your web server is running, let's say, mit.edu, and then you set up a CNAME for that mit.edu to machine1.mit.edu. It's another name. And then someday you decide to change from machine1.mit.edu to machine2.mit.edu. All you have to do is to change this one mapping in the back end in the DNS that maps from mit.edu, set up a CNAME mapping to a different machine, and that's all you have to do. You don't have to tell anybody else about the change that you've made. So it's very useful. And this is a more general, this is just an example of a more general concept that we've seen already called a synonym. And the fourth thing, which is actually what we're going to spend most of our time on today, for the rest of today, is called an NS record, which is a name server record. And this is the thing that's really going to help us figure out how to implement DNS resolve in a scalable way. I'll describe what a name server record is in a moment. So if you look at this tree, associated with labels in the tree, associated with many of the labels in the tree are not just A records, which are generally associated, but also things called NS records. And what an NS record says is that, let's say that there's an NS record associated with mit.edu. What it says is that that NS record gives the name of the machine that's responsible for managing all of the names that end with mit.edu. So for example, edu wouldn't know anything about, in general, edu may not know anything about how csale.mit.edu is really mapped. But all edu needs to know is what the NS record is for mit.edu. So that when it then, as you'll see in this procedure, you'll see that occasionally things at the top of the tree will get requests for a given name, and then you now need to know what to do with the full name. And the way they'll do it is they'll find out that they don't know anything about the full name, but they know about other people who know more about that name. And that's going to be implemented using this thing called an NS record. So I'll show this with an example, and I think it'll become pretty clear. So the way in which applications use DNS is you have an application that wants to call DNS resolve on a DNS name, and there's a piece of software that usually runs on every computer called a stub resolver. Okay? And a stub resolver is just something that allows applications to not have to worry about this whole RPC mechanism that DNS involves, that DNS entails. So that's just abstracted away into the stub resolver. So the stub resolver really does all of the work. So the way the stub resolver works is, and the way DNS resolution works is that the stub resolver really can send a DNS request that it has from the application to any name server that it wants to. And later on, we'll talk a bit about how you pick this name server. And there are lots of these name servers around on the internet. It's a massive distributed infrastructure, and the infrastructure consists of of nodes that have responsibility for different portions of this namespace. So you send a request to any name server, and they all participate in the system together, these name servers, to help resolve names. So let's take an example here. Let's say it's x.csale.mit.edu. So at this point, in general, the name server knows nothing about x.csale.mit.edu, and its plan is going to be that it's going to send this request out to the root name server. Okay? And for now, assume that the root name server is well known. That is the IP address of the name server in charge of the root. So everybody has a name server record associated with themselves. Assume that the IP address of the name server of the root is just well known to everybody. Okay? So it sends x.csale.mit.edu all the way to the root name server. And the root name server is actually going to look at this thing and say, well, you want to know the A record. You might want to know the A record for x.csale.mit.edu. It says, well, I don't actually know what the IP address associated with this name is, but I do know somebody who can tell you more because I do know who runs the name service for edu. So it comes back with a response that's also called a referral saying, well, I don't know the answer, but here's where you need to go in order to find out more. And that's done by sending back the name server or in fact more generally a set of name servers, but sending back the NS records for nodes that handle the EDU domain. So that just comes back at you, and now you now know one or more name servers for the EDU domain. So let me write that here. And this name server then goes back to this EDU domain and says, okay, tell me what it is. Tell me what the IP address for x.ccl.mit.edu is. And notice that at all stages it's sending the full name, because there's always some chance that these nodes have the answer, and we'll get to why that might be in a few minutes. But you always send the full name, and the EDU name server record in this case is in general going to say, well, I don't know about x.ccl.mit.edu, but I do know that MIT came and delegated from me, so I do know the name server record associated with MIT because it delegated from me. And in general, everybody has to know the name server records for the people one level down from them. So it sends back this information saying, well, I don't know what it is, but here's a referral to the name server for mit.edu. And this procedure basically continues. So this is MIT, actually it's just the mit.edu name server. And you just go back and forth until eventually you get to the name server for ccl.mit.edu, which by definition maintains the mapping for everything of the form name.ccl.mit.edu. And so you get the answer. Or you get something that says X is not actually registered, in which case you get a no such domain error message. Actually, it's a no such domain error code, which you then interpret as saying, okay, there is no such name that's been registered. Now, there's a couple of things of note here. The name server records associated with the domain really have to have very little to do with that domain. In fact, the name server record for the root names, forget the root names for a moment. The name server records for the EDU, the name server records for the EDU domain don't actually have to end in EDU or don't have to end in anything that relates to EDU. In practice, in fact, today they're of the form, something.nstld.com. I mean, they have nothing to do with the EDU domain, and this is an important point. You could associate here any label, any name server name, any name of a name server that's willing to manage the delegation, manage the entries in your database. They don't actually have to match the same domain name. And this is a very powerful feature of the namespace, of the way DNS works, because it's not like this thing has to be something.edu, and here the name server record, the name servers for mit.edu have to be actually something.mit.edu. In practice, edu is not managed by anything.edu. It's something, nstld.com. In practice, it so happens that mit.edu happens to run its own name servers. That's something like bitc.mit.edu, but that's by no means a requirement. So there's a couple of problems that we need to now solve about this basic mechanism. Because what we saw was that once you know the root name server record, then you could go back and forth because everybody knows how the names one level down from them have been delegated and knows the name server entries for those delegates. And then you get the final answer. So there's a few things we need to solve. The first one is bootstrap. There's actually a couple of aspects of this bootstrap. The first one is how does this any name server here know the IP address, know the name servers of the root? And the answer here is that there's no magic. I mean, the roots, you just have to know. And in some sense, in all naming systems, ultimately there is, at some level of this name discovery procedure, at some level there's out-of-band machinery that has to get in and be involved. And the way this works out is that people publish the name server records for the root. They post it on websites. They publish it on mailing lists. And you configure, DNS software is configured to manage those entries. And there are proposals and protocols for automatically updating it and so on. But you got to be very careful with technical solutions like that because you want to make sure that people don't, malicious parties don't pretend, that they're telling you the correct name server entry, because then once they usurp the DNS functioning, they could do a lot of damage. In practice, in fact, DNS is not particularly secure. It's a different discussion as to whether that's important or not. But The way this root name server mapping works is that everybody just knows. It's widely published. You go to Google and you'll just find the answer, or it's also on all sorts of mailing lists. The second, so this is the first one is root identity. The second issue is, how does a stub connect to any name server? Would it just pick a random, how does it find the name server that it can connect to? And the answer to this is that, this is actually running on your computer. The stub resolver is running on your machine. It's a library in your machine. So one approach, and this is the most common approach today, is that you might obtain it when you obtain an IP address using a protocol like DHCP, where you turn on your computer and you get an IP address using some protocol. That protocol, some gateway upstream might tell you which name server to use. So if you have a computer at home, your internet service provider would have something set up, so they would tell you what name server to use. So this could be done using a mechanism like DHCP, or like in the old days, and these days, if you sort of you want to do this kind of work, it's done manually. For example, you could go into some registry somewhere or a file like resolve.conf, and you just type stuff in. The second issue that we need to spend some time about, and we're going to spend the next 5 or so minutes on, is performance. And the main point about performance is that if you look at that picture for how names are being resolved, if somebody at Berkeley wants to resolve x.csale.mit.edu, there's a huge number of round trips that they have to do to all sorts of name servers all over the world, or at least all over the country, before they can figure out what the IP address is for my machine. And this is a little bit silly, because often they might want to connect to your web page and get a 4 kilobyte thing, which takes about a couple of round trips to get. And in order to do that, they're spending a huge number of round trips, huge latency in getting this right answer. So the approach that we're going to take to solve the too many round trips problem is an approach you've already seen. We're going to use caching. And in order for this caching to work, there's actually something in this picture that you have to understand in a little bit more detail about two different kinds of name resolution that are really going on. The first kind of name resolution that's going on in DNS is the kind of resolution that the edu name server or the mit.edu name server is doing in this picture, and that's called iterative resolution. Iterative resolution says the following. If I ask you to do some work for me to resolve a name, you just tell me, if you don't know the answer, you just tell me, I don't know the answer, but you go here and find out the answer. So you're getting these pointers referring you to the right place. The second kind of resolution that's going on is the kind of resolution that this box is doing, this any name server box. And it's doing something called recursive resolution. Because what's going on here is the stub resolver is telling it, here's a name, resolve it for me. And what he's doing is basically saying, okay, I'll resolve it for you and get you the final answer. I'm not going to give you a referral back to other places. Which means that eventually, once it figures out the answer, if there's one, it's going to know the answer, even though it did not originate the query. And the moment you have recursive resolution, it means that you can cache the answer. Because if somebody else comes and asks you the same query, you already have the answer cached. And notice that this benefit doesn't accrue if you're doing purely iterative resolution. If everybody was just sending referrals back to the stub resolver, the only caching you would really be gaining, primarily be gaining, is for all of the requests that are common to this computer, because nobody is actually caching, getting any answers along the way. Nobody's even getting any referrals along the way. They're only getting, only the node that's starting the name resolution is going to be getting any answers or any referrals at all. So the secret to getting good DNS performance is for certain nodes, for certain name servers, to agree to do recursive resolution. And an example of that is any name server in this picture. So now if you have a lot of computers here with a lot of applications running on it, all of which use the same name server, and that name server is configured to recursively resolve names, then that name server benefits from being able to cache the answers to previous DNS lookups. But notice that they can cache two kinds of answers. and one of which is much more important than the other. The first kind of answer they can cache is the final answer that you get back that says x.csale.mit.edu is at a particular IP address. So the next time somebody goes to x.csale.mit.edu, they have the answer right there. But if you look at the statistics of DNS requests, there's some commonality in that everybody wants to go to www.cnn.com or google.com or yahoo.com and so on. But there's a huge number of requests going to machines like yours and mine, which aren't running anything interesting, and we're the only people interested in those machines. So really what's going on and why caching helps is that not only are the final answers being cached, these referrals are being cached. So for example, any name server already knows the root, but now after the first request, it knows the mapping for edu's name service. And after the second one, after the first one to mit.edu, it can cache the mapping for mit.edu's name server as well. So the next time somebody asks for anything.mit.edu, this name server doesn't have to go all the way back to the root. In fact, it doesn't even have to go all the way back to edu. It just has to start with mit.edu, whose name service entry it already has in its cache. And that really is the reason why the DNS scales very, very well. It's because it does caching, but the real key is that it's caching referrals. It's caching these name server entries associated with these labels. It's getting some benefit from caching the final answers, but it's really gaining a lot of benefit from caching referrals. Now, of course, when you cache things, you have to worry about things being stale, because you certainly don't want to cache it forever. If you cached it forever, then nobody could change anything. So how do let's say you decide to change the mapping of www.mit.edu's A record from one IP address to another. How do you tell the whole world that you've changed it? Well, there's two high-level strategies for this. One is to somehow keep track of all the people who've cached it and invalidate entries. And a few lectures from now, we'll look at ways in which that kind of approach might be made to work for different systems. DNS deals with it in a different way. It doesn't worry about invalidation. Instead, it sets expiration time on entries, also called TTLs or time to live. That's sort of a abused and overloaded term in networks, but it's really an expiration time. It says that here's the answer to any of these questions, to a referral or to the final answer. Here's the mapping, and it's valid for such and such a time. Okay, like it could be anywhere from 15 seconds or 30 seconds to 3 hours or a day. Usually it's a day or two. It's usually never more than a couple of days, because you reach the point of diminishing returns. One request every 2 days is not a big deal. So, usually it's on the order of, several seconds if you want the mapping to be fine-grained, or an hour or a day. And after that, any access made after that to the same entry, whether it be a referral or whether it be a final answer, has to go back to the server that's authoritative, that's responsible for that entry. So, for example, if you went for the first time doing a lookup of this name and you got back that mit.edu's name service was some name and that it was valid for an hour, then the first request that happens for anything.mit.edu from here after an hour has to go here. I mean, edu, assuming that edu is still a valid, hasn't yet expired, this entry has to go here. So if you look at a time sequence of when you go when you actually go back to the server responsible for a name, you can kind of divide up time into these chunks, which are the expiration time intervals, assuming they don't change. They're set by the server. And then you might have accesses in between like this. And if you look at the only accesses that go to the server responsible for the name are the first ones after every TTL, after every expiration. So in terms of this is the basic story for how you get reasonably good performance and save a lot of round trips in DNS. And the real reason for the scalability of the domain name system is a combination of administrative delegation. So you don't have some human being involved in every name that's being added to the network. It's distributed across different organizations. And the fact that you have caching, in particular, you're caching these name server records, which means that you can save a lot of load on the root and on the edu or com name servers. Originally, the designers of DNS, one thought that they had was that DNS would scale very well because the namespace is extremely divided and hierarchical, which meant that you were gaining a lot from the hierarchy, and that's why it would scale. But that's actually not true, because more than 90% of the domain namespace is not hierarchical in any deep sense. Everybody is something.com. Everybody of importance is something.com, or wants to be something.com. And so, most of the load gets here. So there's no real deep hierarchy that you're benefiting from here. That's usually some flat name.com. But it's divided, and it's delegated. And that's the really nice thing about it. So you're gaining much more from the fact that it's delegated. You would probably gain the same scalability if everything were just something.root. Okay? We didn't really need too much of this in terms of scalability, although it's very convenient to be able to do delegation. But primarily, it seems to be universities that take advantage of this kind of a depth here. Most companies tend not to pay much attention to depth, but yet the system scales because it is, in fact, administratively delegated. So one word on replication. The DNS name servers responsible for these names are replicated. There's, you can't set up a DNS name and have a name service associated with it. A DNS name server record has to have at least 2 entries, and they have to be on 2 different networks. And that's one way so that if one of them is down, you can get to the other. And unfortunately, it turns out that that simple rule is often violated. Probably the most celebrated incident here was Microsoft's update site, or one of those sites was down for more than 24 hours, and in the end, turned out, like in all these cases, to be a complicated set of reasons for why it failed. Nothing fails for a simple reason. But one of the root causes was that they had DNS name servers that were replicated, but they happened to be behind the same Ethernet switch on the same subnet, which is not recommended, but that's what they had. So it's the kind of thing that you need to be careful about doing. So I'm going to stop here, and from Wednesday we will talk about fault tolerance. The recitation for tomorrow is a very short paper about called Google and 9/11. But tomorrow you'll see a little bit about how Google works.